All right, get a laptop now. Stop bubbling. I'm weaning you off the bubble phase. Go get a laptop now. Use your legs and walk over to the laptop cart. If you do not finish bubbling, it's okay. You'll put it in the box later. I'm going to scan them today sometime. If you didn't finish bubbling, put it in the box later. If you don't have all of it done, I'm just going to score the ones you have. Basically, this is feedback for you for study purposes. You just have to look on the front, negative back. You gotta get the happy, different. Use them. Alright, I need your attention up on the board in like 10 seconds. So, log in on the computer because you know they're slow. We're just trying to get that thing pulled up. It's Friday. It's like, I don't want to do this either. Okay? I will pull up my IMF notes. I'm just going to add on a couple of just little details because you guys already have a great background. You have great notes on that. So if you'd like to do it on the same sheet of paper you guys did on, what, Monday? No. Tuesday. Remember that one IMF worksheet that you guys took notes from my PowerPoint? Yeah, the one I actually did. Alright, last call. I'm going to start. Have this out. I think that you should have all your IMF stuff together just so you're not like working from 5 different places. So IMFs are going to, this is the sheet that you got on Tuesday, and it says Interim Molecular Forces Review Worksheet. You took notes on it from a PowerPoint. Alright, cool. I think we're on the same page. Are we? Thank you. Okay. So IMFs lead into our next unit. So we've touched on them to get a good idea of how they can impact all the properties once we determine the polarity of a molecule. So once we determine the shape, we can determine the polarity. Once we determine the polarity, we can determine the, no. Once we determine the shape, we can determine like where the electron lone pairs are versus the ligands, we can determine the polarity. Once we determine polarity, what do we have the power to decide? The intermolecular force, LD, LDF, DD, or HB, or if it's ionic, it does not have an intermolecular force. Eventually, when we start getting into solutions, yeah, we'll go into ion dipole and a little bit more of those like kind of miscellaneous ones. But I just wanted to add a couple of details because in our lab that we're starting, just barely starting today, but we're doing hardcore on Monday and Wednesday next week, it's going to be helpful to be able to talk about IMFs a little bit more confidently than maybe we feel right now, okay? So for London dispersion, you know it's the weakest. London dispersion forces are present in all molecules. Check. It's the most predominant force in nonpolar interactions, but it is still possible in all interactions. It's just not the most predominant force. Another thing you should know is the polarizability word. Who are my LDF people when you guys were jigsawing? Okay. So the polarizability word just means that you have an electron cloud, and in that electron cloud, there are electrons, right? And you have the ability to shift your electrons to one side or the other just because electrons can move. So if they all shift this way, what do we create over here? A partial negative, just a temporary partial negative, but it is there. And then because of the movement of electrons to the right, what does that create over here? A partial negative, positive, partial positive. So essentially, if you have more electrons in your cloud, you can do that more significantly. You get a bigger partial negative and a bigger partial positive than something with just a few electrons in the cloud. More electrons, more polarizable. Check? Okay. That essentially means your London dispersion force gets stronger. That's all that means. Alongside of that, we did not get into this number 4. We did not get into this piece because we're not dealing with structures like this just yet. But things like organic structures. What's an isomer, Christian's group? What's an isomer?
Very similar to something else.
Oh, okay.
Resonance structures, yeah, very similar to resonance.
Can you elaborate?
It can be like modeled in different ways.
Okay, I'm stop. That's good. Okay, stay there. I don't want you to get off track. So resonance structures have atoms in the same place, bonds in different places. Okay, so that's what we talked about when I was talking to them earlier. Isomers have the same atoms, but in different places, right? So the structure is different, the formula is the same. Okay, so if I have pentane, I've got 5 carbons, right? 5 carbons can be aligned in a line, so it's like just a linear pentane strand. You can have isopentane, where you have 1, 2, 3, 4 carbons in the line, and then one kind of branches off. So it's an isomer of pentane. And then you can have neopentane, where it's like a T shape because you have 3 and then 1 branch and then 1 branch. So it still ends up being 5 carbons. So those are all isomers of pentane. Well, if you just look at pentane, you're like, oh, you know who's going to have the strongest London dispersion forces? You don't know because they all are exactly the same, all exactly the same formula. So you must consider their structure. So the points of contact that an individual pentane linear one can have with another pentane, these are all carbons, okay? The point of contact is all happening right here. So that's where the London dispersion force would occur. That's a lot of contact. So think of it like a line. They can stack, 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 stack. So they have a lot of contact with each other. That would be a really, that would heighten their boiling point or melting point or whatever we're talking about here. But this one, kind of like a little flower, okay? When you put that next to another one like itself, yeah, kind of like that. There it is. How much contact's there? Less, right? So there's just a little contact there. It's just harder to arrange a branch structure up tight close to another one. So who's going to have the higher of the melting points in this comparison? The N-pentane, not the neopentane. So that's just another point that we'll start to discuss maybe a little bit in next week, but more so in our next unit. So that's it for London. I just want to do reminders there. Really, there's nothing new with dipole-dipole or hydrogen bonding. Who's the strongest of the ion mass? Hydrogen bond. Well, in this case, hydrogen bonding. Who's even stronger? Ion dipole. And that's only in aqueous solutions, or in solvents, because we have to have a solvent kind of creating some sort of dissolving of the ionic compound. So otherwise, these will increase in their strength based on the molar mass present in the individual compounds. We good? Okay, go to my website. I want to share one more thing with you, but it's nothing really big because you guys have already done all this. Yeah, nope, that's it. That's all we're going to do. I go to the classwork link. It's under homework for today. Just to keep it easy, you can find the same thing. It says electron glue. So I did not print this part for you, but the idea is that you have a good background already of the characteristics of ionic, network covalent, which is kind of new. Can you grab that? Thanks. Metallic and molecular covalent. So covalent structures, those are like simple covalent. Oh, they're so nosy. Thanks. Alright, so we have a general idea of what these characteristics are. Note that network covalent is something that we will discuss a lot more in our next unit, but network covalent compounds are still bound in a covalent fashion, but they're huge. If there's an array, there's a network of covalent bonds. Molecular covalent is just a simple covalent compound. It comes in 2 flavors. It can be a polar molecule that's covalent or a nonpolar molecule that is covalent. So that's just a little bit more there. But essentially, you're going to go through this activity, and you got to do this with a partner, and you got to write some stuff down. So grab a piece of paper, grab your laptop, and come home. And there's a little bag. You can put yourself in a little bag to work with. How many of you have it? Yes, I'm going to bring a laptop. There's questions in the Alright, get settled for me, and everybody scroll down to, I think, probably the fourth page, where it says 4 models of bonding. You see the 4 models of bonding. those procedural steps, read the handout for 4 months on the study the information on the sublinks part. Your job is to match each sublink to its appropriate bonding type. The sublinks part that we're at has the middle back is clear. Just follow the instructions. Go find another group. Oh, there's another guy. I don't know that.
And your total is $38. Sorry, $28. You saved $10 with Beeline's new Shop and Earn program.
All right, come on, guys. Let's roll. Bags in the little blue basket. Butts back up here with your laptops, please and thank you. It is. And pull out your lab sheet that I provided you yesterday. The little inquiry lab sheet that I provided for you yesterday. And I will come and just look at 1 through 9 to just give you your credit for that activity for today, okay? So just keep 1 through 9 on your desk. Just at some point in time today, if you've not put your bubbles in the box, then please do that so I can score those and give those to you Monday. And then I know you're still on my website because eventually some of this text is kind of small on your paper. So I want you to be able to look at it if you need to on the big screen. So you have your lab out from yesterday. We you on that one. All right, so essentially what our lab is called, what's the lab called now? What's the lab called? What's in that bottle? So the premise is I'm giving you a substance in a bottle, and you're about to figure out what it is. Now there's, I don't know, billions of molecules and compounds like I could give you, so that would be pretty unfair. So I provided you with a list, mostly what's in the bottle. So there's a couple that are off script. That's just because I got crazy and started some things in there that weren't on the list. But before you can actually approach the lab, you have to first be very familiar with all the properties that you could be testing for. So you got a good idea from the little electron glue activity, because you know what things dissolve and maybe what they look like. If you had a microscope and or a magnifying glass, you could see some of those structures. Some things are so small we couldn't see them, but we could test for their properties, right? So if I'm testing for something, I put it in water and it's electrically conductive, what is it? If I put it in water and it's electrically conductive, ionic. If it's just by itself electrically conductive, metallic. Are ionic solids electrically conductive? No, why? Because why? It's not necessarily, it doesn't matter if it's neutral. Electricity has to flow. And so if electricity can't flow between two stagnant ions that are not able to move, electricity can't flow. So in the aqueous form of ionic aqueous solutions, then they can flow. Okay, so you have a couple of pre-lab questions that you're going to approach first. On Monday, I'm going to do the teacher-directed lab with you. I'll give you 4 substances. And with those 4 substances, I'll guide you on how you can test for their properties to show that they are ionic, metallic, polar covalent, and non-polar covalent. Notice I excluded what? Network covalent. 1, there's only a few of them out there. 2, it's really hard to test for them. So we won't be dealing with that just so much right now. But I want you to do the pre-lab questions first. Go ahead and work in the groups that you're just sitting in right now. You can write this on paper or you can type it up on Google Docs, okay? So there's just a couple of pre-lab questions. Oh, if you can't see that text, go to Unit 10. If you can't see this text, go to Unit 10. And you'll see the big screen. I've already pre-designed your lab groups for this activity because I've just put people in different groups and roles. So this is just a quick activity, so don't spend too much time on Google Labs because this is not who you're going to be with. There are like 2 pre-lab questions. This will not take you more than 5 minutes. Eventually, you will have to draw all these structures in the second table, so I would still have some paper available to do this with.
I actually would have been disappointed if it was The data table in table 1 is what you're basing all this off of.
Does 19 mean like this, the molecules like away from each other? Does it mean like we should
That is not melting. You know, melting is a physical process. So, well, I mean, but it depends on if you're talking about an atom, like iron is an atom, but like you wouldn't melt and pull carbons from hydrogens because that would be a chemical change. That would be a decomposition reaction. That's not melting. So that terminology is not consistent. You got me though? Yeah. All right, you should have the table done in part 2. You should have it done very shortly. All right, let's review these. That's why I was trying to get you guys just to get the main points done and versus making Google Docs, but you are fine on that. For the rest of this, I'd like for you to either write something down on your lab sheet, and when I ask for you guys to draw the part 2s, I'm going to help you with that, but I do need you to actually draw them, okay? So compare the type of bond with regard to the properties below and explaining the relationships, melting point and solubility, right? So Qui, can you guys your group get me started on the relationships with melting point? So are you saying that a covalent bond or a covalent molecule? Because, and this is a conversation I just had with somebody else, when you have a covalent structure, let's just say carbon bonded to some other stuff in here, and I melt it, this bond is not breaking. Because what if I do break that bond, if I break it apart to make carbon separate from carbon, just add those like that, what have I done? Say again? Well, that is true, but I haven't melted it. What have I done to it? I broke a bond. I didn't melt the compound. What did I do? No. I changed the chemical structure. I've made a chemical change happen. Melting is not a chemical change, right? Melting is a physical change. We cannot change the structure of anything. We're just overcoming attractions so that something that's really close together, but now it's just farther apart. We never change the chemical structure. So that would be like a decomposition reaction, okay? So that is not what we're talking about. We're not talking about a covalent bond being overcome or a covalent bond breaking. But a covalent molecule, one of them is attracted to the other one via how? Say again? Any IMF, right? So I'm just going to put IMF here because it depends on the type of compound. So a covalent compound is going to be held close to another covalent compound, to another covalent compound, to another covalent compound via really weak IMFs. We know, like, oh, hydrogen's the strongest of all IMFs, but it's got nothing on an ionic or metallic bond. Those are true bonds. Those are intra-molecular forces or intra-particle forces. They're super, super, super strong. This is super, super, super weak comparatively. So these are going to have relatively relatively low melting points or boiling points. I'll just kind of relate that to boiling as well. Because when we actually do this process, we're taking this and this, we're saying, nope, heat them up, speed them up, pull your cells apart. So this covalent molecule is now way far away from this covalent molecule. So what have I overcome? This small attraction they had, right? So I've melted it. Maybe this was the solid phase, and then I made it go to liquid phase. Okay? Chemical structure does not change. Now, group, can you guys give me more for question 1? Excuse me? No, for question 1, give me more. All I got is covalent so far. Ionic has what? High melting points because why? Okay, so why do they have a strong bond? Why does it make it stronger? Keep going. Okay, so positive, there's a full-on positive and a full-on negative attraction here, right? So why does this differ than this? I'm going to go back up here, because if we just mentioned covalent, we didn't mention polar or nonpolar, right? So for polar compounds, or polar molecules, what do they have on their structure? Partial positive negatives, right? So I'm going to put the partial, how's that blue stuff? Partial negative over here, and a partial positive here. This will be a partial negative, this will be a partial positive. Okay, so with respect to what's attracting here, It's a partial positive and partial negative, right? And they're kind of far apart. Whose law am I trying to pull in? Coulomb's law, right? So with this one, you have a partial positive and a partial negative is your Q1 and Q2. It's just partial charges, not full positives, negatives, or positive 2, positive 3, that kind of thing. And their distance is relatively large because their interparticle space is just farther away than an ion could be to another ion. So for this one, you have a, let's say it's magnesium sulfate, right? 2 plus, 2 minus. Automatically that attraction is way higher than that. And what's good, what do you know about their distance comparatively? Smaller, right? So this was a bigger distance, this is a smaller distance, so we have a double whammy on the attractive forces. So the electrostatic attraction for an ionic bond is super strong compared to the interparticle attractions for a molecular IMF. Okay, and then metallic, nope, it's still working on melting. Okay, why are they high melting points?
Because they're all attracted together.
Say that louder so we can
So
hear.
like they've got like their delocalized.
So you've got your positive cation cores, like this is silver, silver plus, and you have an electron floating around, right? But this electron is a full negative charge, this cation is a full positive charge. Their distance is going to be relatively close as well. It kind of depends on where the electrons really are, but they're still really close to the cation. So I'm just put ditto. It's really similar to this. That's why ionics and metallics have the highest melting points. They do vary a little bit, like magnesium sulfate might be 2,000 degrees Celsius and iron might be 1,500 degrees Celsius, but they're really high. Okay? Solubility. All of this still relates to solubility, all these little partial positive, partial negative stuff. Who is insoluble in water? Okay, why? Okay, what's water look like? Okay, it's bent, right? It's polar structure. So H, O, H. Water's got its little partial positive here, right? And a partial positive. Can a partial positive, do you think a partial positive can or pull apart this and this? Good to know, right? Our cars do not melt in the rain, right? They're not going to dissolve in the rain. So the positive of the partial positive cannot compete with a full positive for this attraction. Not very well anyway. If you have a lot of water molecules, eventually you could like eat it away, but it would be like oxidation or something happening instead. With ionic, soluble or insoluble in water? Always soluble? Well, we have those insoluble products, right? Precipitates. So I'm going to say many times they are soluble, except for when this attraction is so large, like aluminum phosphate or silver phosphate, or things like with a 3 charge, a lot of times are insoluble products, so are precipitates. So most of the time we can have water overcome this attraction. It is still a very strong attraction, but you don't have a network like this has. This has a lot of electrons around a given cation. In an ionic compound, you only have just to give a set number of electrons around the, or set number of anions around the cation. So water can do some damage there and get it to dissolve. Now, dissolve and ionize are 2 different things. This one will ionize, right, to make ions. This will not do anything. What will water do to polar molecules? Dissolve them. Does it ionize them? No, because first of all, there's no ions. 2, it doesn't actually pull the molecule apart because that would be a chemical change. Ain't not going to happen. So this is going to be, this is a lot of times going to be soluble because it, like sucrose was the example, it has to have a part of the molecule that is polar to attract to them. So in the other case, a nonpolar, would it be soluble in water? No, not very well anyway. So insoluble. Now, you can't always tell if something's dissolving. You might have to do some tests to see if it is, because it might look like it's not, but then you might do some tests to see if it really is. So that's where we're working with our lab. All right, so that's the first question. Second question, draw hexane, okay? Very similar to what we did in class with the pentane. What's hexane look like? You're thinking benzene. Oh no, this one is hex. Well, okay. I'm gonna show you both. Okay. Okay. So with this one, I'll show you bromobenzene first. So benzene is what Cassie was just saying, the little ring. Can you guys see that? Okay. This light is out, so I don't have my picture ability to see. Okay. So it's 6 carbons and 6 hydrogens, right? So each of these vertices is a carbon, and then when you put your double bonds in there, it creates some stability, and then there's hydrogens hanging off the carbons. You guys remember this a little bit? Yes. Okay, so this is benzene, which in this case is our hexane ring, but it's not actually called hexane. This is a typo with this name here. So looking here, obviously covalent, polar or nonpolar. Why nonpolar? Balance. So you're saying equal distribution of electrons. So this is nonpolar. Okay. So you should be able to determine the characteristics about that. Relative melting point, high or low? Relatively low, very low attraction, very easy to overcome. Solubility in water? No. Okay. So bromobenzene, notice it's C6H5Br. There's only one difference here. I'm going to pop off one H and add a what? Add a Br. So you have the strong. Draw the next one. Bromobenzene. I'm just going to take off one of the hydrogens. I'm going to put a bromine in its place. What does bromine need around it? Octet, right? It needs lone pairs. So give it some lone pairs. Okay, and then talk in your group for a hot second. Decide if it's polar or non-polar. Everybody should be drawing these structures as I asked earlier, so that you have something to base your lab off of. So this right here has a partial what? Partial negative, and this all over here has a partial positive, so therefore it is a polar. Bromobenzene is polar. So it can do what with water? Can dissolve, and then relative melting point, higher or lower than benzene? It's a little bit higher than benzene. It's not going to be like thousands higher, it's just going to be a little bit higher because it's still covalent, so it's still relatively low. Sodium chloride? Sodium chloride? Ionic, relative point, high, like super high, and then solubility? Yes. And then iron. So metallic and high and no. So with iron, just so you're aware of what that looks like, you have, let's say it's iron 3 plus. It's going to, be in a lattice of sorts, and it's going to have 3 electrons surrounding it. But those electrons are free to move because they're not stagnant, they're not static, they're not localized. Yeah.
So that's the way we would draw it if they told us to.
Yeah. I mean, you could make it a little bit more elaborate, but essentially you've got electrons floating freely. Okay, laptop's up for me, okay? I'll take to do at the end here, but we're not going to work on lab anymore. We'll wait till Monday. Make sure they get logged off, okay? Yeah. No, they put hexane on that last. That's just what it's called on here. Because hexane should be C6H12. This is C6H6. They probably put that there because most people don't know what benzene is. So just call that benzene. C6H6 is benzene. No, I'll see him later. I didn't get to see him. I thought I'd get a chance to see him, but this took longer. Because you actually might need a little bit of that for the lab. Because you got like the properties on there.